Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the Raoults law of the liquid in liquid type of the solutions. In our previous classes, we have already discussed the vaporization, vapor pressure and the boiling point. Now let us see how by mixing two different liquids having different vapor pressures influences the boiling point, as well as how there is a change in the interactions between the molecules. All these we are going to discuss in the today's class. So let's begin the class. Raoults law for liquid in liquid type of solutions. So in this case, we need to take both volatile liquids, means which are able to form the vapor, both solute and solvent. So let us take the two individual beakers in which let us take the two different liquids. So in the first beaker, let us take the liquid A, and second beaker, let us take the liquid B. Both are different. Liquid A forms vapor and also exert the pressure on its own liquid surface. That vapor pressure is coming only from the pure liquid of A. So this vapor pressure is called as the P0A, pure liquid vapor pressure of A. Similarly, liquid B also forms the vapor on its surface, and also this liquid exerts the pressure on its own liquid surface. So this vapor pressure is called as the P0B. So from this it is clear that both liquids are able to volatile, means they are able to vaporize so that they can exert the pressure. Now let us mix both of these liquids in a common beaker which forms solution of A and B. So both liquids are present here. So A and B. Now this is to be called as the solution, not the solvent. These two are solvents. Why? Because mixture is present and homogeneous mixture is present. Imagine both liquids start evaporating so that they form the vapor. So these are the, whatever the circles I am going to mention, imagine these are the vapor molecules coming from the A liquid and the dots coming from the B molecule. Now the vaporization is a surface phenomenon. More the number of molecules present in the liquid, so more it can go into the vapor state. That means if A composition is more in the liquid, so that A molecule get the chance to go into the vaporization. Why? Because more A molecules will occupy the surface area. If B liquid is more present in the solution, then B liquid molecules will occupy the surface area so that they get the chance to go into the vaporization. So let us imagine these are the A liquid molecules and these are the B liquid molecules, liquid B. So which molecules are more here? A liquid molecules are more than the B, so that A liquid molecules are going. If you take opposite, that B liquid molecules, then B molecules also form the more vapor. So whatever it may be, this is called the vapor pressure of the solution, and the pressure coming from this vapor is known as the vapor pressure of the solution of A and B. So in this vapor pressure or vapor, both A molecules and B molecules are present. The vapor exerted by the A molecules is called the partial pressure of A, and the vapor pressure exerted by the B molecules is called the partial pressure of B. Why it is called as partial pressure? See, the total pressure is coming from the both A molecules as well as the B molecules. In that, a part of the pressure is coming from the A molecules and rest of the part of the pressure is coming from the B molecules. So that part of pressure is called the partial pressure. So whenever a particular molecule is exerting the pressure, whenever it is present in the mixture of the components, the pressure coming from such molecules are called the partial pressures, because remaining molecules will give the remaining pressure. So the partial pressure of A depends on how many A molecules are present on the surface area. More the number of A molecules means more shall be the partial pressure of A. So here is more the A molecules are present, in the sense more mole fraction of A is present. So that we can say that partial pressure of A is directly proportional to the mole fraction of A. Similarly, the pressure coming from the B molecules we call it the partial pressure of the B. That depends on number of B molecules on the surface area. If more molecules are there, more shall be the partial pressure of the B. If less molecules are there, less shall be the partial pressure of the B. So that the partial pressure of the B molecule is directly proportional to its mole fraction. Now, let us try to replace this proportionality symbol using the constant. That is, partial pressure of A is equals to P naught A into XA. Why we have taken the P naught A here? P naught A is nothing but the pure vapor pressure of the A, which remains constant at the particular temperature. And similarly here for B also, partial pressure of the B is equals to P naught B into mole fraction of the B. Let us consider this is the equation 1 and this is the equation number 2. Now total pressure, according to the Dalton's law of partial pressures, total pressure exerted by any gaseous mixture is equals to the sum of the partial pressures of all those gases present in that mixture. So total pressure is nothing but the pressure of the A molecules and the pressure of the B molecules. Now let us try to substitute these two values in this equation. So we get that P total is equals to P naught A XA plus P naught B and XB. So this is the one of the form. Now the question is, what is the meaning of XA and XB? Here I said that more the vapor means more shall be the A molecules in the liquid. That means here XA stands for the mole fraction of A in the liquid phase, XB stands for the mole fraction of the B in the liquid phase. So here we can write down that XA equals to mole fraction of A in liquid, XB equals to mole fraction of B in liquid phase. So both are in the liquid phase. Now let us try to expand this equation. We know that XA plus XB, sum of the mole fractions always equals to 1. So in the place of XA, we can write down 1 minus XB. See here, you can take in the place of XB, you can write down 1 minus XA. Any form is possible. So that you can write down any of these. I am taking XA equals to 1 minus XB. So that the total pressure of the vapor pressure of the solution is equals to P naught A into 1 minus XB plus P naught B into XB. So now let us expand again this equation. P total is equals to, just multiply it, P naught A minus P naught A XB plus P naught B XB, and this can be written as P total is equals to P naught A. So plus form I am writing the first and later minus form. So plus P naught B XB minus P naught A EXB. So in these two forms EXB is a common, so that I am taking out. So P total is equals to P naught A plus P naught B minus P naught A into XB, mole fraction of the B. So now let us try to draw a graph between the P total versus XB. So it comes in the y equals to mx plus c form, so that whenever a graph is drawn like this, on y-axis if you take total vapor pressure, and on the x-axis if you take the mole fraction of the B, then the graph comes with a positive slope where intercept value is equals to P naught A, and this slope is equals to P naught B minus P naught A. So if the slope value is given, we can calculate P naught B, because slope is available as well as intercept value P naught available. So P naught A can be substituted here, as well as slope value can be substituted here, so that we can calculate the P naught B value. Similarly, let us try to see another graph for this equation. So this graph condition is, let us imagine one of the solvent is more volatile than the another solvent that is in the solution. So I am taking here P naught B is more than P naught A. That means B liquid is more volatile than the A liquid. You can take A liquid is more volatile than the B liquid also. Anything can be taken. So let us draw a graph. So one side let us take the A liquid, other side let us take the B liquid, and this y-axis, in both are these are y-axis, this is x-axis. So y-axis says about the vapor pressure, and here mole fraction of A equals to 1, mole fraction of A equals to 0, here mole fraction of B equals to 0, here mole fraction of B equals to 1, and XB varies this side. So what is the meaning of this? So it clearly says that XA equals to 1. Remember, for any particular solution, sum of the mole fractions value is equals to 1. Mole fraction of A plus mole fraction of B. If 3 are there, means mole fraction A plus B plus C equals to 1. Then here XA equals to 1, in the sense 100% is only A liquid is present, B is not present. Then on this line we cannot call this this particular one, we cannot call as a solution, we have to call it as a solvent. So solvent means we have to represent its vapor pressure with the P naught. Which compound is present? A is present, so that we can call this one as a P naught A. Now when you go from left to right, A completely becomes 0 at this end point and B becomes 100%. That means A is not present, now only B is present, so that's why it is called the liquid B. Now the vapor pressure on this particular line is called the pure liquid vapor pressure of the B. Now condition here we have already taken that B vapor pressure is more than the A vapor pressure, so that it has to come little upper line. This is equals to P naught B. Now let us apply these formulas. According to this formula, partial pressure of the A is directly proportional to the mole fraction of A. When mole fraction of A increases, partial pressure of A also increases. When mole fraction of A decreases, partial pressure of A also decreases linearly. So remember here, in this particular line, only liquid A is present, that's why we represent it as a P naught A. Once you step out of this line, then A mole fraction of A is not equals to 1, it shall be less than 1. Why? Because 100% A is not there. Why? Because B concentration gradually increases. So between these lines, whatever the present, that is called the mixture of the components, so or else we can call it a solution. So whenever solution is there, in the solution the pressures should not be represented as P naught, but it has to be represented with the PA, because partial pressures, because they are in the mixture. So now this pressure of the A gradually decreases, because A value decreases and becomes 0 at this end point, so that partial pressure of the A gradually decreases and becomes 0. So on this line, what we can calculate? We can calculate partial pressure of A at any point. So partial pressure of A is equals to P naught A into mole fraction of A. At any point we can calculate the partial pressure. So it clearly says that if you want to calculate the partial pressure of A at this particular point, and at this particular point, let us take 2 points. So at this particular point, partial pressure of A is high. Why? Because mole fraction of A is high. That's why partial pressure of A is high. And at this point, if you want to calculate partial pressure, it is less. Why? Because mole fraction of A decreases completely. And similarly with B liquid, initially here B liquid is 0, so that it does not have any partial pressure. Once after stepping out, gradually mole fraction of B increases and reaches the maximum at this point, so that the mole fraction increases and partial pressure of the B also increases. Now this is called as the PB, that equals to P naught B into mole fraction of B. Why? Because now B not only present, A also present along with the B. That is the reason why between these two lines we have to call it as a solution. Now what about the total pressure? Total pressure is the sum of the PA and PB at any given point. So that total pressure, if you add PA plus PB, so gradually it is going like this. So here we can get that total pressure of the solution equals to sum of the partial pressures of the A and B. And what other information we can grab from this particular graph is, all lines are giving linear graphs. So here partial pressure of the A linearly varies with its mole fraction. Partial pressure of the B also linearly varies with its mole fraction. And total pressure of the vapor pressure of the solution also linearly varies with both XA and XB. How it is linearly varies with the XA and XB? See, if in terms of the B, if you consider, so total vapor pressure increases by increasing the B. Why? Because here P naught B is more than the PA, P naught A. So B is more volatile than the A. That means total vapor pressure always linearly varies with the compound that is more volatile than the other compound. So that's why total vapor pressure linearly varies. Now, so from all these concepts, we can calculate the P naught A values, P naught B values, total pressure, mole fraction of A and B in the liquid phase. This is liquid phase. Then, how to calculate the mole fractions of A in the and B in the vapor phase? So, according to the Dalton's law, we know that partial pressure of any compound is equals to mole fraction of that compound into total pressure. Remember, this is not applicable to the liquid, this is only for the gas phases. So now we are going to apply the gas phase. So in the gas phase, mole fraction of A, I am going to consider as the YA. So partial pressure of A equals to mole fraction of A in the gaseous phase and a total pressure. Why I am taking YA instead of the XA means only to differentiate this XA with this XA. Otherwise, we get confused that mole fraction of A in the liquid phase and gaseous phase shall have the same notations. That's why I am replacing this XA with YA. Similarly, partial pressure of the B is equals to mole fraction of the B in the vapor phase into total pressure. Now, how can we calculate YA value? So, YA, mole fraction of A in the vapor phase is equals to partial pressure of A by total pressure, total vapor pressure. So, partial pressure of A, that means P naught A XA and total pressure, you can write down either PA plus PB, or else you can write down this one P naught AXA plus P naught BXB, or else you can write down this one. Any of these forms can be written. So I am writing PA plus PB. This is mole fraction of A in the vapor phase, and mole fraction of the B in the vapor phase is equals to P naught B XB divided by PA plus PB. So like this we can calculate the partial pressures of the various composition of the liquids in the solution state when they are in the mixed. So I hope you understand today's class. So we shall meet in the next class. Thank you one and all.